It is very frustrating. I don't have any cop to call, but it's very frustrating.
Okay, I know what you mean.
Yeah, it's very frustrating. So, what it's worth. Okay, so we're talking about stars. We talked about we talked about characteristics of stars before, and now actually you're going to hear me kind of refer to that video that we watched a lot, so I don't have to spend as much time in lecture. So stars live their lives and then they die, and it's based upon basically how much mass they start with. This actually is the death of a star, the kind of the graceful end of a star. It's a supernova remnant. Some stars blow up, but they're massive enough, and that's what this star did. Okay, so one of the things actually I think the video talked about was that, and we talked about too, was that this idea of a cluster of stars. There's two types of clusters of stars. There's open clusters and globular clusters. Basically a bunch of stars born about the same time. Stars are born about the same way that our sun came into being, okay? Remember when we said that our star came into being, something called the nebular theory? Okay, we can see that as stars are born, many stars can be born in the same chunk of dust, okay? A nebula is a chunk of dust. Our sun and our solar system and the planets came out of what we call the solar nebula, okay? We call a large chunk of dust that actually can birth, and we're going to see some photos here in a minute, a chunk of dust that can give birth to many stars at one time, these clusters of stars. We call that actually a molecular cloud. Yeah.
For chapter 13, it's different than yours.
Okay.
It's 147. I did that too.
Keep my sense of humor. Madison's got it.
Yeah, I got it. I was on there.
There's 213s.
I don't have anything to say about that. I just assume that we're all, adults, and we all kind of are here and do what kind of the instructor asks to do for the course, and it all works out in the end, and if it doesn't, it doesn't. So molecular clouds, actually, we're going to see some pictures of caught in the action stars being born, a bunch of stars being born at one time. But in order for a star to be born, basically, like the video said, gravity needs to kick in, okay? Just like within our own solar nebula, gravity needs to kick in order for a sun to be formed. So molecular cloud was the term I was talking about. This actually is an example of a molecular cloud. A molecular cloud is just a giant nebula. This is actually, there are bright nebula and dark nebula. This is a good example of kind of a dark nebula. We're coming up on Halloween, so I don't know if you kind of see this sort of ghosty looking kind of shape right here. Kind of looks like an amoeba, sort of, okay? It looks dark. Okay, a dark nebula actually is obscuring the field of stars behind us. Because can you see, we have a field of stars back here, okay? Dark nebula is where these, actually it's a molecular cloud there. Lots of stars can be born about the same time. So here's another kind of stellar nursery, another molecular cloud where stars are being born. So we talked earlier, kind of off and on in this class, about the idea where energy needs to be conserved, and one way to actually convert potential energy to kinetic energy is for something that's big to become small. And that's what's happening as gravity kicks in and these regions start to hopefully become stars, and maybe even planets orbiting the stars. So it's a balance, just kind of like the video said, and kind of within our own sun, it's a balance between gravity making our sun smaller and basically kind of the energy from our sun making it kind of fluff out. The term protostar, like a prototype, means kind of a type before the real type. So protostar is the star before the real star. So protostar hasn't yet turned on. And so kind of these baby stars, if you love babies, you can put a little smiley face there, okay? Little tiny baby stars. They glow, but they don't have nuclear fusion going on. So the best we can do actually is kind of see them in kind of the subtle regions of energies, infrared. So kind of from left to right, this is not a photograph. This is actually kind of showing you how you can start with a molecular cloud. I lost my red pencil. Okay, so this is your MO cloud, molecular cloud. And one of the things, I don't know if it's a slide that I've already covered, but actually, in order for kind of these little nits to form within your molecular cloud that can turn into stars, you need some sort of external energy. A lot of times it could be two clouds bumping together. It could be like a bright star here, basically kind of shining and creating these nits. But your molecular cloud needs to have some fragments, and these kind of little fragments in here, these little things could actually are budding stars. Okay, so fragmentation happens within the molecular cloud. This can be our stellar nursery. This could be a cluster of stars that are born under the same molecular cloud. So protostar then is basically that tiny little bud, oftentimes born in a stellar nursery where other stars are being born too. Just like we said that our sun basically had a little bit of rotation, our solar nebula had a little bit of spin to it. Okay, that spin had to be conserved. Okay, so as it got smaller, it's kind of like an ice skater bringing in her arms. Okay, our solar system began, our sun began spinning faster and faster, and actually that conservation of what we call angular momentum was kind of conserved also in the planets orbiting the sun. So this is kind of revisiting our sun being born. But one of the things, and actually I have some photographs down here, that these are photographs. This one over here on the far right was a figure. One of the things that can happen is it's still a protostar, still a baby star, not yet nuclear fusion in its core, is basically, and you can see this disk right here, hopefully planets are being born right here, right? And actually kind of perpendicular to its disk would be kind of these jets of energy. And we can actually see those captured in other stars. That's pretty cool. So the protostar, it hasn't yet turned on. So we talked about HR diagrams in chapter 12, and we'll be talking more about HR diagrams. But an important feature of HR diagrams is that diagonal. We call those main sequence stars, and so I'm kind of building up to that. So protostar is a baby star. It becomes a full-fledged star when it begins nuclear fusion in its core. So that's actually this third line here. When the temperature and the pressure is hot enough in the core of these protostars, then it will begin nuclear fusion. And we talked a lot about nuclear fusion with our sun, just to kind of remind you, just put simply, I guess you take 4, H stands for hydrogens, okay? You squish them together, high temperature, high pressure, and you end up with actually just 1 helium and energy, E for energy, and gamma, and a few other things. Okay, so when this happens in the core, actually it creates what we call solar wind. Well, solar wind, just stellar wind, right? Okay. The stars have stellar wind, our sun has solar wind. And it basically kind of clears the dust out. The jet would go away, basically. Any planets to be seen will be seen then at that point. Okay, so it arrives at what we call the main sequence on the Hertzsprung-Russell diagram, on the HR diagram. Yeah. And I'll go ahead and note it this way, where it talks about, I do have I have the unit exam made out, okay, that you'll be taking next Wednesday, so I have a review sheet to give you on Friday. I've already posted the review sheet under Doc Sharing. But gravitational equilibrium, we said for our sun, actually was a homework question for that chapter on the sun. Gravitational equilibrium just basically says gravity is wanting to make our sun come inward, and basically the energy that the sun is exerting is gonna want to go outward. All right. Now again, I kind of feel like, we kind of set the stage for stars in general. Do you remember we talked about O be a fine guy, kiss me, the 7 spectral types? Okay. So the O is the hottest type of star, and of course the M is the coolest type of star. So just to kind of remind you, and actually this is something we talked about earlier before, those hot stars, they actually have more mass, but they live shorter lives. And we're going to see that, we would see that on the HR diagram, make use of that. So the video talked about this, when a whole bunch of stars are born at one time, kind of how many stars do you get of each type? Well, you get a lot more of these M-type stars. Okay, I'll put M down there. You get a lot more of those than you do of the hot OB-type stars. So kind of superimposed under this would be OB, fine, guy, kiss me. Okay, kind of backwards, where this is actually the coolest. So you get a lot more of those dim stars. But like they said, we don't see those because they're so dim, darn dim. So again, something we kind of talked about, I'm going to reinforce this as we talk about the lives of stars. There is a limit on how massive a star can be and the lowest mass that an object can become a star. So the high-end mass, we said 100 solar masses. Actually, we can have stars up to 150 solar masses. But if they're too big, that little chunk that is a protostar that wants to become a main sequence star, it basically just can't settle in. And it just kind of blows itself into smaller pieces, and then it becomes a star, hopefully. Okay. On the other end of the spectrum, we said that the low end, basically, 8% times the mass of our sun would be kind of what you're looking at. And that is a critical mass because anything lighter than 8%, no, that's fine. So anything less than 8% of the mass of our sun, actually, it tries to go ahead and create the temperatures and pressures it needs in its core, but it never can to go ahead and fuse hydrogen into helium. So it actually has a cool name, though. Kind of those failed sort of stars are actually called brown dwarfs. And we're going to talk here in a minute something called, we have a lot of dwarfs. We have white dwarfs, brown dwarfs, and red dwarfs. And actually, I've heard of black dwarfs before, too, just recently. Maybe it was on the video. So a brown dwarf is a failed star. Basically, it was a little nit of something that got hot, was a protostar, but never had enough mass to basically begin thermonuclear fusion in its core. Failed star. So in here, we're going to talk coming up as stars live their lives. And honestly, when we talk about black holes, this is important too. Mm-hmm.
So does a failed star, so does it give off heat and stuff then?
Yeah, it just kind of gives off like oozy sort of heat, like infrared. So yeah, you'll see brown dwarfs, and I think actually this one right down here, this B, those little circles indicate where we have detected a signal from brown dwarfs, but it's just like the subtle thermal energy. Yep. Subtle thermal energy, not the thermal energy like from a star.
Would they still be too hot to physically step on it?
Yeah, they would. They would still be too hot to physically step on. But that's a good point. They will eventually kind of radiate their thermal energy away, and as far as I know, at some point they would cool down and you could step on them. Yep. If you really wanted to.
I guess that was kind of where I was trying to figure out too,
Yeah.
I don't know if they're hot or not.
Yeah, they start out hot and then they cool down. But we are a lot about basically kind of squishing things. It's funny because actually the video talked about, it's a fight. The gravity keeps squishing stuff together. So we talk about something called degeneracies, a various assortments of degeneracy. So here it just says degeneracy pressure stops the squishing of a brown dwarf. So degeneracy pressure is basically just saying you have this object and this object, and they can't share the same space. Okay, and we're going to talk about electron degeneracy and pressure, but it just stops. And they liken it to kind of like if you play musical chairs. It's kind of a silly sort of, but I've seen this kind of in other textbooks. This, basically you have a room with all sorts of chairs to sit in, Okay. Then as gravity kicks in, the space becomes less, and then you have a room with basically more people than chairs. And at that point, basically, you're done. The same person cannot occupy the same chair. Okay. Or excuse me, two different people. The same person can occupy the same chair. Two different people cannot occupy the same chair. That's degeneracy pressure. Okay. So I kind of now need to break out into basically low mass stars and high mass stars because they have two different life cycles. We're going to do that, but then also we're going to take low mass stars and we're going to take low mass stars and kind of do one other thing with them. Okay. So it's all about mass. Basically, what track you're going to be on. So in order for this discussion, for most discussions, I'm going to go 8 times the mass of our sun. 8 solar masses, that's the cutoff point. So anything less than 8 solar masses is a low mass star. Anything heavier than 8 solar masses is a high mass star. Okay? So this actually has a series of bullets, and I'm going to kind of give you a glimpse at how a star lives its life if it's 8 solar masses or less. 8 solar masses or higher. Okay, 8 solar masses or less. How does it live its life? Well, we talked about this already this morning. Okay, this idea that basically it's a protostar and then it turns on when it begins nuclear fusion in its core. Okay, at that point we actually call it a main sequence star. What we haven't talked about, and actually one of the video on the sun talked about this. Okay. For these low mass stars, and by the way, if 8 solar masses is our cutoff, okay, can you see where 1 solar mass, actually our sun is a low mass star, okay? So this is one of the things our sun is going to do. Basically, it's going to run out of hydrogen to fuse into helium, and it's going to swell. And we looked at HR diagrams, and we'll be looking at them again today, but if this is our little HR diagram, okay, along the x-axis, we said you can just go ahead and OBAFKM, GKM, final answer. Okay, that actually is from the hottest to the coolest star. And then we said along the y-axis, we said actually this is brightness or luminosity. Okay. And then we went ahead and put in our line, what the heck, and we said that actually stars that are on this line, these would be stars with this particular luminosity and this particular temperature or stellar type. These are what we call our main sequence stars. Okay, and then we said up here, these are called our giants and supergiants. I don't know, there's a subtle difference. But both of those I'll just call giants. Red giants, super red giants, that's where they are. So here's the deal. Can you see where basically if you were to come from main sequence, and our sun is going to do this, our sun is about maybe here. If you were to come main sequence and come up, okay, if this is where our sun is now, when it comes up here, what is it? Well, it's still our sun. But can you see, do you buy this where it has more luminosity, increased L, okay? And it's basically got the same surface temperature. But usually, I should say, it's going to go, instead of there, it's going to probably go more like here. So it's going to increase luminosity, more luminosity, and actually it's going to be cooler. Because it moves that way. So anyway, that is a red giant stage. Bless you. I have a figure coming up here to kind of show you what I mean by shell hydrogen fusion. That's kind of, after it swells, shell hydrogen fusion. Now, one of the things that low mass stars will do, as long as they're not low mass stars, is they actually in their cores will take that helium, which they created when they were main sequence stars, and begin fusing it into carbon. Okay, so that is actually what our sun will do. So our sun will end up as basically an orb of carbon, and it will kind of have a new life. then actually it will run out of helium to fuse into carbon, and it will cool and contract. Two more things yet for our sun to do, okay? Well, I don't know necessarily to do. The corpse will end up as what we call a white dwarf, a retired star. And on the HR diagram, I won't do the whole HR diagram, but here's my mini HR diagram. White dwarfs, if this is main sequence, white dwarfs are right down here. That is your white dwarf, which means it's low luminosity and probably still kind of warm. Back to your thing about the brown dwarf. White dwarf, brown dwarf, okay. The white dwarfs will cool off, and you can maybe even go stand on those too, but they're pretty hot at first. All right. So I said that our sun is actually going to go ahead and fuse helium into carbon. That's what this is showing you. Helium, the red arrow means going to form carbon and energy. Okay, so it will do that. This is kind of a blow up of kind of the red giant stage of a low mass star. Okay. I mentioned shell hydrogen fusion, and that is right here. So the thing about shell hydrogen fusion, I know it sounds kind of weird, but basically you have a helium core, okay, because that's what it made when it was a main sequence star. Then around the helium core you have fresh hydrogen, fresh H, and when the darn thing starts to fall in on itself, because it does, because it's no longer a main sequence star, basically this becomes hot enough to go ahead and begin shell hydrogen fusion. All right, so HR diagram. Along the x-axis, you see the hot stars, the O-type stars, and the M, the cool-type stars. You see, we've been talking about, again this morning, the main sequence would be right here. Okay, that would be our main sequence. We talked the other day how massive stars leave the main sequence first. So actually, all of these guys have gone, and it is an indication of the age of the cluster of stars. This is the turn-off point right there. So you see stars up here would be your red giants. Stars down here are your retired stars. Basically, they go up, become red giants, and then they come down to become white dwarfs. That is a low mass star. So again, an HR diagram, kind of showing you what I showed you. Picking the sun, for example, moving off the HR diagram up into this region. This actually shows something guess, this is all about it. I thought I had a slide on this. Something called a planetary nebula. These look great through the telescope. I'll show you some examples of planetary nebula. Planetary nebula are beautiful. Basically, what's happened is a star is on its way to retirement, okay? And on the way, it's going to go ahead and just kind of give off the stuff it worked so hard to collect. Okay, those are dying stars. In the center of these planetary nebula would be a white dwarf. So I said 8 solar masses is kind of the cutoff, but there actually is a low mass star that the video talked about called a red dwarf. So low mass stars have to be at least 0.08 solar masses, but if they're like somewhere between a half a solar mass or 0.4 solar masses to 0.08, then this is what they do. We talked about convection in here, and that's kind of a key to a red dwarf. Convection, we said, is basically warm stuff moving up and cooler stuff sinking. So what's convecting here actually is helium that's created. It's a normal star. So main sequence stars have hydrogen fusion in their core, and they're creating helium, which kind of gets in the way, and it kind of builds up, and they run out of hydrogen, and they do some other things. Well, if they're light enough, basically, one way to look at it is they're not like crammed, they're not as dense. So basically the spent helium can convect out and fresh hydrogen can convect in. Okay, and that's what's happening. So basically fresh hydrogen comes in to go ahead and keep that process going on in the core. So it ends up with just basically, it will never go to the next stage. This low mass star will never do the whole helium into carbon. I'm reconnecting. All right, so that was low mass. So 8 solar masses is kind of the cutoff, aside from kind of that 0.08 to 0.4. Okay, so high mass stars, what do? Well, something a little bit different. They start out the same way. Okay, we talked about a stellar nursery, the protostar, to a main sequence star. Okay, and they will expand once they leave the main sequence. Okay, but they will generally become supergiants instead of red giants. It must be a small detail. I don't know. So they get big, but they don't stop with just fusing helium into carbon. They take it the next notch. There's something called CNO that stands for carbon, nitrogen, oxygen. So in the video, do you remember where the so the lady was the light star, and the other gambler had a bunch of chips. Remember the gambler, the guy with a bunch of chips? He was like the massive star. So he basically went through his fuel very quickly. And one of the ways massive stars can do that is actually kind of having a different mechanism for nuclear fusion in their core. That's where this carbon, nitrogen, oxygen cycle comes in. Massive stars run through their fuel very quickly. And like I said, they don't just stop with fusing helium into carbon. They go after that. They continue after that. But it's true that when they have their helium all converted to carbon, then you're like, okay, I got a core of carbon. What am I going to do next? Well, they go ahead and contract, get hot enough to fuse carbon into something else. Okay, that's just what they do. So carbon will be fused into heavier elements. This carbon, nitrogen, oxygen cycle down here, I don't know how well you can see it, but actually, for instance, we have, I was going to say, I guess it's carbon, nitrogen, and oxygen. Heavier elements, all within stars. So, kind of like the video said, it kind of, it definitely goes in stages. It's not random at all. First you have the hydrogen fusion into helium, then you have the helium fusion into carbon, then you have the carbon fusion into, I believe, oxygen. But heavier and heavier elements are being formed. Carbon fusion into neon, excuse me. Neon's the major element. So I put this slide together to kind of show you kind of what's the next step. Now, all stars are a little bit different, and this actually is based upon a star that is 25 solar masses. 25 solar masses, definitely on the heavy side of 8 solar masses. Okay, and then I actually put how long they take at that stage. So, hydrogen fusion, main sequence star, long time. I'll just put a long time. I don't have the time there, but okay, longest time. Not as long as the sun, but I wanted to emphasize these. How long does it take, for instance, to go ahead and in its core convert carbon to neon? 600 years. How long does it take to convert neon into oxygen? 1 year. How long, when its core has oxygen, does it take to convert oxygen into silicon? 6 months. Okay, when it has silicon, and like silicon, like the video said, when it actually is fusing silicon into iron, iron is kind of a dead end. How long does that take? 1 day. Like, really, that's short in the life cycle of a star. So what's up with iron? Okay, well, I'm going to show you here in a minute, but just like the video said, you end up with kind of this onion-like structure where you have the heaviest elements in the core, and then you have these shell fusions, kind of like we have hydrogen shell fusion. So it's just amazing. Definitely looks like an onion. The problem with iron is, and the video said this, the problem with iron is if you try to take two iron atoms and put them together, the nuclei of two iron atoms, put them together to make something heavier, that's actually what we call an endothermic reaction. It would require energy instead of releasing energy. That's the first element that does that. It's kind of a tipping point. One of the things we talk about nuclear reactions, we talk about nuclear fusion, which is what stars do, and we also talk about nuclear fission, which is like what uranium does. You take a big old uranium atom, it falls apart pretty good, and basically you convert some of its matter into energy. That's fission, right? So iron would be that tipping point. It would more like to fizz than fuse, okay? So there you go. So the problem is the star needs to do something here. So the star's going to blow up. The star's definitely going to blow up when basically the silicon has been converted into iron in its core. It's on its way out. So with regard to the whole kind of converting, the whole fusion process, this slide talks about that. We're going to talk about in the next unit, we're going to talk about kind of the beginnings of our solar system, or we talk about the beginnings of our solar system. We're stepping it up. In the next unit, we're going to talk about the beginnings of our universe. And we've already talked about the fact that our universe was basically born with just hydrogen. Okay, just hydrogen. There's the periodic table. And of course, we are a carbon-based life form, and we definitely have all of those elements. All of those elements came about because of stars living their lives.
So, like when I was saying about the brown dwarf, every planet is has all the same elements, right? Like there's no new elements that could possibly that we just don't have on our planet, kind of thing.
Yeah, that seems right.
Okay. It's like
Other planets.
Avatar, on a different planet, you look at this floating magnetic orb. I just didn't know if there's new stuff out.
Yeah.
I don't know.
Yeah, you're right. And like Star Trek, sometimes they'll throw in new like dilithium. You're like, what is that? It's like,
Maybe
it's
from a different galaxy, wind will just break through our barrier. It's like here's new
Matter,
stuff.
Matter could be based on something other than just an atom. But in our things made of atoms have centers, and that anyway, there are only a certain number of elements, and there they are. Yeah.
I believe there's one more. It's a secret one. I'll find it.
It would be something other than probably the atom like we're used to. So, but I don't know if you remember back when we were talking about atoms, these kind of red and black things, that's are actually the center of atoms. Those are the nuclei of atoms, and the different colors come from the protons and neutrons. Okay, so basically they're showing the fusion of carbon to create silicon. Fusion of a carbon atom and an oxygen atom to get silicon. Oxygen to get sulfur. Yeah, silicon and silicon to get iron. There is something interesting this chart right here is saying how abundant are the elements. I believe it says in the galaxy. So this kind of goes back to what you were saying about there being some sort of secret element out there. They kind of come in twosies. Kind of the even-numbered elements are most abundant. So atomic number is the, let's see. Anyway, the even ones are more abundant because they kind of come in pairs with the helium capture phenomenon. All right. So when silicon fuses into iron in just, what'd I say, one day? How many? Okay, 1 day in a star that's like 25 solar masses. The whole iron thing is problematic. Okay. So when it can't fuse iron into anything heavier and get energy out of it, okay, it's like, all right, then that outward pressure that we have going on in our sun, because it has fusion going on, that ceases. So basically, gravity wins out. So it's no longer at equilibrium. Gravity's going to win out, okay? It's going to collapse in on itself. And here's where we have kind of a different sort of degeneracy going on. Remember I said with a brown dwarf, this different people can't occupy the same chair sort of thing. Well, the matter tries to come in and squish down, get smaller, become more dense. And so what happens actually is that, can you see this P is a proton down here, and the E is an electron. Okay, so we definitely have protons and electrons within the core of that star, okay, are converted into N as neutrons. So basically you take proton and electron, you squish them together, and you get a neutron and a neutrino. So that's what's happening at the last gasps of this star, okay? So you get a neutron. And here in a minute, I'm gonna show you for these massive stars, okay, the final result of a massive star's death actually has two options, okay? One option is actually what we call a neutron star, and they are real. It's an awesome sort of thing. Neutron star is basically neutron soup, okay? You're like, what element is it? Well, it's a subatomic particle. It's neutrons, okay? The other option, and by the way, a neutron star is basically, if you were to look at the sharing of the few people sharing chairs, basically what's supporting the whole mass of that core of that star that didn't blow up in supernova is basically neutrons bumping against neutrons. Neutrons bumping up against neutrons. Over here, normal matter. What separates normal matter from atoms from sharing the same space? Well, it's the electrons. It's electrons bumping up against electrons. So what we say electron degeneracy is normal matter. Neutron degeneracy here. Well, if the neutrons can't really, there's just too much gravity is basically compressing that object to the point that neutrons cannot hold it up. Okay, basically the fabric of space and time collapses in on itself. Okay, and you end up with an object, okay, that's not a neutron star, this is a black hole. Okay, so if neutron degeneracy fails, you get a black hole. So there you go. All right, in the meantime, okay, amidst all this commotion, basically you have, how do I say this? Stuff running into the iron core, and the iron's not going to compress anymore. Basically, that stuff coming in hits, if you've ever taken, if I could take a ball and throw it against that wall, what would the ball do? It would come back, yeah. That's exactly what's happening. So basically, you have all of this stuff running towards the center, it hits a brick wall, and it rebounds, it goes out. So the stuff coming in didn't get the message. So basically, you have stuff coming in, stuff going out at the same time. You have just a crazy commotion during this explosion, okay? Now, that sort of coming in, coming out creates all sorts of hot spots that actually can finally, it's called nucleosynthesis, okay? That sort of coming and going creates other conditions for more nuclear reactions, even heavier than iron. Because you're like, well, okay, how do we get anything heavier than iron? And this is how we got it, okay? It's called nucleosynthesis. So that is M1. That's the Crab Nebula. Remember we talked about Messier objects, okay? So yeah, this is actually, if you've seen my YouTube channel, this is the little icon I have for my YouTube channel. And it's got like a picture of it's called a supernova, so it's like Superman, it's got a little cape. Yeah, anyway. So in the center of that actually is a neutron star, creating what we call, actually we'll talk about this, what we call a pulsar signal. So that's the guts of a massive star that died. And all sorts of, we should mine that, right, for heavy elements. Here's another sort of actually catching the supernova in action a little bit. So this is what this star looked like before the supernova. This is what it looked like after the supernova. Okay.
Is there color added into that first picture, or does it look like that,
I
actually?
think it actually looks like that. Yeah. That's pretty. So this is a busy slide, okay, but let's see, kind of orient ourselves. Let's start with the bottom part of the slide. This actually is low mass, not low mass, but this is what a low mass star will do. You recognize kind of maybe the protostar here, kind of the little jets of energy, main sequence star, red giant. It basically reestablishes an equilibrium. It will burn helium into carbon, that's fine. Then this over here is the planetary nebula. This is the planetary nebula, and there's a little white dwarf. Okay, so that's low mass stars. The one at the top here, very similar. See, to me, if I compare them kind of side by side, to me, I kind of got up there is about the same for the high mass stars. Okay, this doesn't emphasize it, but it does end up with kind of like an onion-like in its interior sort of structure. But this is showing you how a high mass star is blowing up, and then over here, it ends up with, the two options over here are either we said a neutron star, neutron star, or a black hole. And we'll be talking more about those in the next chapter. So one last slide, and it seems kind of miscellaneous. It's weird how it is, but it's going to tie in with the next chapter on stars. We said that, and actually the video too said that most stars actually have a companion. And so this is actually talking about how a set of stars that are gravitationally associated with each other. And stars kind of have, it's possible to have companions that are different sizes. So here, this is maybe a high mass star. Call this a high mass star. Okay, and we'll call this a low mass star. And one of the things we know is that low mass stars take a lot longer to live their lives than high mass stars. Okay, so high mass star potentially can reach its kind of bloated stage. The cool thing, and again, we'll talk more about how this relates to something really interesting, but if they're close enough together, some of the stuff from the bloated star can actually fall into the stuff on the companion star, and that's exactly what's happening here. The real example, and I think we looked at this star the other night when we had the telescope up. If you look in Perseus, Perseus saved Andromeda, and also Perseus is holding Methuselah's head, the one with the little funky snakes coming out of her head. Okay, and she has like an eye, and then actually that eye is called Algol, and that's exactly kind of what's happening here. So what can happen is that low mass star actually can kind of go through a different stage than we're used to seeing it. Here it's kind of puffing up into a higher, more massive star. I'm looking at slide. Very good. Okay, so this chapter will be due on Friday. Very good.